The next speaker will be is a professor from Loughborough University, UK. Professor Yogachandran received his PhD degree in Signal and Information Processing in Loughborough University in 2020, then worked as a postdoctoral fellow for 6 months on encrypted signal processing techniques for privacy and preserving multimedia big data processing. Subsequently, he joined City University, London. So, over to Professor.
Hiya, thank you. Thank you for the introduction, and thank you so much for inviting me to this talk. Thanks to Balaji. Let me share my screen. I hope you can see my slides. Like Dr. Prabhakar, I like to keep my slide not in a presentation mode so that I can see what's happening as well. Right, okay. I got 20-25 minutes. Let me crack on with the presentation. I had a question for the previous talk regarding the RSA and qubits because the talk I'm going to deliver is pretty much, kind of complement what Professor Prabhakar presented. Right. So this talk is about machine learning in encrypted domain. I'm a senior lecturer at Loughborough University, London, so the outline of this talk will be motivation, some examples, why machine learning, what are the problems exist, what type of encryption techniques we can use, and some state-of-the-art works and conclusions. So before I dive into the talk, I like to present the current view. Currently, what happens when it comes to data is that we are connected with so many cloud service providers. So if you step back, this is what's happening because we are connected with so many cloud providers, websites. Our data actually encrypted in 2 times actually. So the encrypted when it is stored on a device or on the cloud provider, and it is encrypted during the transmission. But the problem is data is not encrypted when data is processed. So the cloud provider knows your data. So if the cloud provider or server being hacked, then the hackers will know the data, right? So that's why we have so many data breaches happening. Just last year we had 20 billion data records, which means on average, every person on the planet lost 3 of their data to the hackers, and this is increasing. The reason for hacking is the data is in the client domain wherever it is stored, right? Because so if you want to avoid this data breaches, we need to come up with a completely different approach. A few years back, if you took any web servers, websites, or any internet communication, they are not protected. They were using HTTP. Currently, more than 99% of communications are protected during the transmission. So we have HTTPS, but as I said before, the data is not encrypted when your data is processed, right? So the way forward is there are a lot of visionaries thinking about is to go for HTTPZ protocol, where data will always encrypted in the storage, in the transmission, and during the processing. And there are, if you know the popular social media platform, they are now thinking about how they can able to deliver advertisement if the data is encrypted all the time. Currently, they are able to deliver advertisement to you because they can see the data, so they know about you, so they can able to send a relevant advertisement. But if we go towards this fully encrypted, end-to-end encrypted system, then the problem is, how they can able to find your attributes so that they can. So there are a lot of things are happening in this domain, right? So the ideal solution, as I said, it will always be encrypted, right? Transmission, processing, as well as in storage. If you have that situation, then data privacy, you don't need to worry about privacy, because the data is always belongs to you. Data sovereignty, you own the data, so and of course there won't be any data breaches. And if we have a situation like this, then a lot of people are willing to share the data. I don't know how many of you still using Facebook. So many people are hesitant to put our data online because of the privacy issue. But if we can able to solve this data breaches privacy problem, then people will be happy to share the data for common cause. So medical data, healthcare data, personal data, financial data. So they can able to put these personal data together to solve some of the issues related to health, if it's a health or environment or whatever it is, right? And another advantage is that if the data is encrypted all the time, then you are not bounded by your jurisdiction. For example, in the UK, the GDPR says is that some of the sensitive data should be stayed within the Europe. Even whether you can use a cloud service provider, they have to host their servers within the physical boundary of European Union so that the data can be stored. So, but if it is encrypted, then you can able to send the data anywhere to do some computation. So you will be able to save some money by finding a cheaper computational power, right? And this is not a philosophy. There are a lot of real applications started to come up. For example, in South Korea, they are actually combining two databases from pensions and from the credit bureau system, so that they can able to combine this data. They can able to process these two data sets in encrypted domain to find the credit ratings for their citizens, so they could able to provide a better financial services to the individuals. The beauty of this one is the people or the companies who are doing this merging between two data sets, they don't know what is actually inside, because it is always in encrypted domain. And Microsoft recently come up with something called password monitor, because so I would suggest you to have a look at this one, right? Right. So one of the another beauty of having this encrypted domain into an encrypted domain approach is that a lot of the when it comes to healthcare, the specialist, the surgeon, they spend a lot of time on going through this X-rays and scan report to find malicious tissues on brain or whatever organ they are scanning. And this process is a tedious process. They spend a lot of time. It's boring, prone to error, and it causes a lot of problems. But the machine learning techniques nowadays is capable of if you send a brain scan, the machine learning approach can able to identify the red spots where the surgeon need to focus on. So it will actually significantly decrease the time. But the problem is these specialized machine learning algorithms are available in a very particular providers, maybe in a different country or in a third party. So the question now is, how you can actually send your patient's healthcare information to a third party without breaching the privacy. If you send it as it is without encryption, their machine learning algorithm is perfect. They can able to actually find the red spots and send it to you. But the question is, how do you do this same thing without breaching privacy? The one way is to encrypt the image and send it to them. And they need to find these red spots within the encrypted domain. So this is one of the application. This is a simple example, but it has a huge potential. So that's what this talk is about. How can we actually harness the power of machine learning without breaching the privacy? When it comes to machine learning, there are two things happen. One is the training process. The training involves quite a lot of data from the application specific data. Then you use the data to train a machine learning model. Once the machine learning model is available, then you can able to infer the new sample using this machine learning model, right? So you will have an output. So this machine learning model will tell whether this particular new data has a malicious or not, malignant or benign. You can able to find out. So now what we need to do is like, for example, let's say if you want to build a simple example to motivate, if you want to build a facial expression recognition model, you can able to find a data set, something like this, and you can able to train it, right? But now what we want to do is actually, we don't want to give away our data to the people. But if we give only the encrypted data, can somebody able to train a machine learning model and provide a service? So that's the question. And the answer is yes, right? And there are two approaches. One is actually, training the machine learning model as well as performing the inference, everything in encrypted domain, right? Or what you can do is a company will train a model and get a model, but they will provide service in encrypted domain, right? And so we will be focusing on the first one, where the model is trained in a plain domain, but it will be inferred in encrypted domain. So what is going to happen is the training will be the same as like before. We will do the training as it is, but once we get the model, the customers or the client will be sending only the encrypted data, right? So if they send the encrypted data, can you able to tell whether that encrypted data, the subject in the encrypted data is happy, angry, sad, or whatever the emotion? This is not just an example. You can imagine any machine learning problem within this context. Okay. So let me skip this one. So we are talking about images, right? But image is an example. You can imagine any data. End of the day, all the data is made of binaries. So we are talking about encrypting it. So can we able to encrypt the data using any encryption techniques? For example, AES, RSA. Can we use any encryption that we know to actually exploit this encrypted domain classification, right? If you want to encrypt, encryption is easy. Basically, the images are based on pixels. You just encrypt pixel by pixel so that you will get an image like this, right? Now the question is, can you use any cryptographic scheme? The answer is no, right? For example, AES, right? You can use AES for encryption, but AES, if the image is encrypted in AES, you can't actually perform any classification, any inferencing, processing on data, because AES, as you know, it will actually scramble everything, right? There is no mathematical relationship. It's just a shuffling. But you can use some schemes like RSA, for example, because RSA has the public key infrastructure is made of mathematical, there's a relationship, so it preserves some homomorphic properties, right? So if you want to use these techniques, if you want to really go for this fully end-to-end encrypted scenario, we have to use homomorphic encryption, right? Homomorphic encryption is something like this, this encryption enables somebody to process the data in encrypted domain, right? So they don't need to see, for example, let's say in this second the image on the right side, there are two numbers, 3 and 4. You use the homomorphic encryption so that you will get some ciphertext, right? So this person in the middle, he can able to compute on encrypted domain so that the numbers on the plain domain will be added, right? So the person who is doing the addition in the middle, he doesn't know what numbers he is adding it, but he is actually adding it correctly. So when you decrypt the output, it will always be simple. So one of the example, let me motivate. RSA has a homomorphic property. This is a very secondary school equation, but there are a lot of things goes underneath. But if you take RSA, just your message, and you raise it by your public key, right? So the message M1 is encrypted like this. If you have another message, this is N2 will be encrypted, N2 to the PE. If you want to, the question is, can you able to compute multiplication of these two messages? If you know the logarithm and power from higher secondary school, we can do this easily in encrypted domain. All we need to do is we need to multiply these two encrypted numbers. If you multiply these encrypted numbers, essentially what we get is encryption of M1 and M2, correct? So we can able to decrypt this one, right? If you decrypt this one, this will be encryption, M1 and M2. So whoever going to do this multiplication, they don't need to know what is M1 and M2, right? As long as they multiply the ciphertext, you will get it. So the problem with RSA is that you can do only multiplication in encrypted domain. So you can do addition, right? But if you want to do any mathematical operation, if you want to go for machine learning, for example, you should be able to perform multiplication addition both at the same time. So RSA is it doesn't. So that's why we call it a partial homomorphic or additive homomorphic encryption. So that's why. And another problem with RSA, as the previous presenter Dr. Prabha was telling, RSA can be or will be broken pretty soon, right? So we need to go away from our classical public key encryption techniques. That's why we have a new encryption technique called fully homomorphic encryption. Fully homomorphic encryption, it supports both addition and multiplication, so that you can able to perform any computation on encrypted domain. And this fully homomorphic encryption is based on new cryptographic paradigm called lattice-based cryptography. And there are a lot of people in Stanford, MIT, IBM researching on this, and they are saying that this lattice-based cryptography is secure against quantum computers. So that's the kind of the state of the art right now. And if you look at the fully homomorphic encryption, the encryption is very simple actually. It's not raising a power or not. You just you get some public keys. The secret key is S, public key is A1, and you just do this linear multiplication and you just add a little bit of noise to it, right? Then you add a message. So this is your encryption and M1. And if you want to encrypt, if you want to decrypt it, all you need to do is you subtract this A1S, so you will get some message plus little bit of noise, and you can able to remove the noise by rounding it, right? And you will do the same thing, right? And this simple equation, what it allow to you is you could able to do both addition and multiplication in encrypted domain without decrypting it. So once you have the encryption and once you have the encryption techniques provide multiplication and addition, you should be able to use this technique to perform any operation on encrypted domain. So if you look at the timeline of this homomorphic encryption developments, it's going back to all the way to 1978. I think that's the time where the RSA was invented, but RSA is like a additive homomorphic. You can provide only one type of operation. But there are active research is going on this. But the fully homomorphic encryption breakthrough happened in 2009, roughly just 15 years ago, by Greg Gentry when he was doing his PhD at Stanford University and working along with IBM. So 2009 they invented the fully homomorphic encryption. Then a lot of research is happening along the line. Currently there are multiple branches to this fully homomorphic encryption. For example, if you want to do, if you know the RSA and things like that, you need an integer, right? Only you can encrypt the integer. If you want to encrypt a double or floating points, then you need to do scaling. But there are some techniques in fully CKKs. It's actually driven by Microsoft. At least currently is being actually the people who invented the CKKs working for Microsoft. CKKs where you can able to encrypt, decimal, floating point, double, any kind of. And there are other. That's one of the stream. Then there are other streams where you will be using integers for encryption. or kind of any kind of you can able to move around between different type of numbers, and it's in a very active research area. So why there are a lot of research is happening is that um, because of the noise we are adding to the encryption, you can't able to perform quite a lot of multiplication. So you are limited to perform like 2 or 3 multiplication continuously. But for example, if you want to build a deep neural network where you are going to have like 100 layers, so you need to perform 100 multiplication continuously, and you have some functions like real, sigmoid, where you can't able to. These are not a real continuous function, so you cannot be able to encrypt or perform multiplication continuously. So what is happening in this fully homomorphic encryption area is like, so when you do a lot of computation continuously, the noise will start to grow. When the noise start to grow, you need to actually refresh that ciphertext, right? So in 2009, when they invented this fully homomorphic encryption, if you want to actually do that refreshing, they are calling it a bootstrapping. It will take 30 minutes, right? So 30 minutes, that was the case in 2009. But now currently we have a lot of advancement in this area. The current is the state-of-the-art technique called Torus fully homomorphic encryption, which can actually perform this bootstrapping or refreshing the ciphertext within 0.10 millisecond roughly, right? So let me put this in a context, right? Because of this, we are thinking about going from doing everything on encrypted domain. There's the cost. The cost that you will pay is like, for example, if you keep the data in plain text, the integer will take only 4 bytes. But if you convert this into encrypted domain, every number will be converted into 1.7 megabytes. So there are almost 400 times expansion. Now, if you want to multiply 2 ciphertext, if you want to multiply 2 plain text in plain domain, you need only 1 CPU operation. But if you do the same thing on the encrypted domain, it will take 12 million CPU operation. So that will increase the time, right? So in order to reduce this, in order to improve the efficiency, this is very, very hot research topic at the moment. If you are thinking about machine learning, have a look at this fully homomorphic encryption, machine learning and encryption. There are a lot of libraries actually. You can imagine IBM, Microsoft, and quite a lot of other startup companies are coming up with releasing new libraries. These are open source platforms, right? Like TensorFlow, Keras in machine learning. There are libraries that is available and could be easily accessible by anyone. So let me put everything in a context, right? So we are talking about machine learning, right? So there is a work done in 2016 by the collaboration between Princeton University and Microsoft. So what they did is they transformed the 5 layers of convolutional neural network to process everything on encrypted domain, and they are using the MNIST dataset. If you know this MNIST CNN classification, if everything in plain domain, doing an inferencing of one image will take a fraction of a second. Right? If you send an image, it will tell you whether it's a number 0, number 1, or number 2. But if you want to do it in an encrypted domain, right, it will consume 400 megabytes of bandwidth, and then inferencing will take 5 minutes of your time, right? But there are, so it's a lot. So imagine fraction of a second and 5 minutes. However, we come a long way. Currently, the IBM has developed a machine learning model with, they actually trained 330,000 logistic regression neural networks, and it took only 20 minutes for them to train, and inferencing took 5 seconds. The current state of the art in this area is like 1.7 seconds we can able to perform inferencing using a very a neural network, right? And I think I am on time. So the conclusion is the fully homomorphic encryption has reached an inflection point where real applications are possible now. And there are a number of libraries and resources are increasing recently. And the bonus is that the fully homomorphic encryption is based on lattice-based cryptography, which is secure against attack coming from quantum computers. And there are a lot of innovation and novel application are yet to come in this domain. So watch this space. Thank you so much. So this is my contact details. So if you have any questions, if you get any questions later, feel free to email to me. I'll be happy to provide any answer.
I want to some clarification. When you are encrypted the data, it becomes completely randomized. That's what my impression is. So training in an encrypted data must take lot more samples for training. Is that correct?
I think your intuition is really correct, Professor Shamshankar. And that is we won't be. The machine learning paradigm will completely change to support this encrypted approach. So we don't use the same algorithms for training it. So because we are mathematically, I wouldn't say it's randomizing the data. We are kind of mathematically transforming the images during the public key encryption. So there's a mathematical relationship, isn't it? So that we need to transform the machine learning algorithms to support that. You can think about like doing everything in a different dimensions, a different domain, for example.
Yeah, that's how I think even the deep learning abstraction may become difficult because of the randomized data.
Yes. So we will completely transform the deep neural network as well. For example, it's just a weighted multiplication, vector matrix multiplication when it comes to deep neural network. So we will change that operations as well to support this encrypted domain classification.
Thank you.
Thanks a lot.